In most mechanical engineering curricula, there is a numerical methods course, a course that teaches students the fundamentals of how to get a computer to perform engineering calculations. The textbook we use for the course is thick. It catalogs 8 techniques for root finding, 8 methods for solving systems of linear algebraic equations, 9 approaches for interpolation and curve fitting, 5 techniques for numerically approximating derivatives, 9 methods for integrating functions, 8 approaches to integrating ordinary differential equations, and much more, including loads of homework problems for students to solve. There are problems which ask students to estimate the derivative of the gamma function. There are problems in which students must determine where within a steel ball bearing the internal stress is exactly half the maximum stress, just in case they wanted to know. At NIU, we are pioneering a new way to teach numerical methods to our undergraduates. We are playing video games. What you're looking at here is the final exam in the course. It's a race. Students had to drive their cars around a track, completing 2 laps in the least amount of time. And when I say drive, I mean drive in the usual sense. We tell the car how much to turn to the right or to the left, how much to step on the gas or the brake. However, instead of using a steering wheel and pedals to give the car its driving commands, we wrote computer programs to do the driving. Sort of like the cruise control in your car, but much more sophisticated. The computer program students wrote had to sense when the car was in a straightaway so that it could accelerate as fast as possible. We wrote the programs to calculate the optimal times to shift gears. Our computer programs had to recognize all the turns in the track and to calculate the maximum speeds at which the car could navigate each. Students computed the last possible moment to begin braking so the car would not spin out of control and crash. It is worth emphasizing that students do not use commercial software to perform their calculations. They write their own software, mostly from scratch. Over the semester, students create and optimize their driving programs to race on a specific practice track. On the final exam, though, they have to race on a track that they have never seen before. Therefore, the computerized drivers have to be sufficiently smart to drive through any turn or any sequence of turns on any surface on any track. As you can see, some of the driving programs are smarter than others. But even the drivers that crash are smart enough to get themselves back on track and to continue racing.
Developers.
In the following year, the final exam was a bit different. As before, the objective was to get the Bizzarini around the track as quickly as possible. But this time the little sports car had opponents. Teams of students wrote driving programs for Humvees whose sole purpose was to slow down or impede the progress of the sports car. Now the Humvees could not simply slam into the sports car. If one did, then it would be removed from the race. Before any collision with the sports car, the defense has to come to a complete stop, just like in basketball. But there's a catch. The sports car cannot directly see where the Humvees are. Therefore, it has scouts, little Volkswagen Beetles, whose purpose is to seek out the Humvees and to relay information back to the sports car. The communication and coordination can get confusing at times. And the Humvees are allowed to do whatever they want with the Beetles. But when it all works, it's a thing of beauty. And when it doesn't quite work, it's still pretty cool. In another class, students are creating a computational model for the car itself. They're learning how to encode the physics of the car and all its interacting components into a computer program. If they build their simulation correctly, the virtual car exhibits the same physical behavior as the real car. It is not easy though. One small mistake can cause the virtual car to do some strange things. Finally, we're using the simulation, as engineers do, to design real cars. The simulation allows one, in effect, to perform many experiments quickly and cheaply. One can explore, for example, how small changes in suspension geometry affect overall handling. And we're not stopping there, we're building the car and we're racing it.